All right, AP class, so today we are doing solubility product of calcium iodate. And it's right up there. It has the dissolution at the top. Calcium iodate solid is in equilibrium with calcium ions and 2 iodate ions. There's your KSP equation. And essentially it is a titration. So we are going to titrate with sodium thiosulfate. So I've got big volumetric flask sodium thiosulfate. And like we typically do when we titrate, I am going to first rinse my burette out. So I'm just going to put some of this in. And we typically don't titrate with this. This is going to be instead of an acid-base titration, we're basically doing a redox titration. So dump that out, empty my tip with the sodium thiosulfate, dump the rest out. All right. So now I'm going to go ahead and fill up my burette with sodium thiosulfate. But this is the only time all year that we use the burettes, when we're not using typically sodium hydroxide. And this is why at the beginning of the year we rinse them out, because we may have used sodium thiosulfate at the end of the last year. All right, so anyways, I'm going to fill it past the 0 mark. Put it over the sink. Make sure all my bubbles are out of my tip. It's below the 0 mark. And then I'm going to write down my volume. All right, so I don't know, 0.043, something like that. Okay, so it's right at the top. The next thing we're going to do is, if you look at the very bottom, I'm going to start adding stuff to a flask. All right, so this is one of those things where I wish you were here to use this piece of equipment. So this is called a volumetric pipettor. Okay, so kind of like a volumetric flask, that line right there is exactly 10 milliliters. Okay, so we use this guy that's going to help get our calcium iodate. And then this is my beaker of calcium iodate. Essentially, it is just the same thing from a year, well, it's probably the same thing from about 5 years ago. There is some solid at the bottom. This has been able to get to equilibrium over the past year. So because there's solid in the bottom, I know it's at equilibrium, and as much calcium iodate that can dissolve is dissolved, and that's why there's precipitate left. All right, so this is at equilibrium because it hasn't been disturbed for an entire year. And what I'm going to do is I'm just going to suck off, or draw off would be a better way to say it, exactly 10 milliliters. So the way this works is, you can't really see everything in the video. So up here, there's like a little, I don't know, this little round thing. As I spin it, it's going to create a suction, and it's going to raise liquid into my volumetric pipette. And I just want to get it from the top of my solution, because I don't want to get any solid in my solution. So I'm being careful to only get it from the top, where hopefully my calcium and iodate ions are floating around. I'm going to draw it until I get to that marking on the pipette, which says exactly 10 milliliters. So this is a more accurate way to get 10 milliliters than using a graduated cylinder. All right, so right there. Take it out. All right, I'm going to stick it in my flask. All right, so the battery died, which is why the video stopped. I have since run 2 unsuccessful titrations, which is fantastic. Tried to record those. So hopefully third time is the charm. So when the battery died, I was in the midst of adding 10 milliliters of saturated calcium iodate solution. So this is what I'm going to titrate with my sodium thiosulfate. If you look at the bottom of the lab, this is kind of the stuff that's going into the flask. So I've got 10 mils of calcium iodate. I'm going to add 0.5 grams of potassium iodide, and that's really what my equation is up here. So I got iodate plus iodide plus some H pluses, so plus some acids, okay, happening. So that is my reaction. So I'm going to add my Ki. So it is about 0.5 grams right here. All right, so I'm going to add it to the flask and nothing happens, and that's completely fine. So I'm going to swirl it around to hopefully dissolve all my Ki. Next, I've got some acid in this graduated cylinder. As I add it, my solution is going to turn like a reddish brown. All right, so this is my starting solution. Okay, so I have the Ki, or potassium iodate, that I want to find the Ksp for, and I'm going to run a series of reactions to find the concentration of iodate. Okay, so we're going to use stoichiometry to find iodate. If I find iodate, I can find calcium. If I know calcium and iodate, I can find Ksp. Okay, so what's going to happen is, in a typical acid-base titration, we're looking for a color change. We typically add phenolphthalein, which is pink in bases and clear in acids. So I'm going to go ahead and start titrating. I'll move this, let's see the color. But what's going to happen is this kind of reddish brown liquid is going to go to just like a reddish liquid. It'll go to orange, then it's going to get to yellow. Once it gets to yellow, I'm going to add some starch. And if you've ever done like a starch lab in biology, if you add like tincture of iodine to a piece of bread, it turns bluish purple. So this is going to essentially act as our phenolphthalein, because it's really hard to tell the difference between yellow and colorless, but it's easy to tell the difference between something dark blue and colorless. All right, so I'm just going to open this up, and we should go from like a reddish brown to like a reddish orange to an orange to a yellow, and once we get to yellow, I'm going to add the starch, which should turn it blue, and then I'll titrate till that blue is gone. Alright, so you can tell from there, but not near as red and dark and brown as it was. I'm going to go a little bit further till I get to more of a yellow. So I'm going to slow down my drops. Alright, still kind of orange to it. Kind of want to get to like a hay yellow. If you have relatives that are on a farm. Yeah, so kind of yellow, kind of like that. So again, it's hard to tell when I go from yellow to colorless, but if I add starch, and I don't need a whole lot, notice my solution like turned black. It's kind of just like a dark purple. So you don't need a whole lot. So now I want to go until that purple is gone. So I know I'm close to the end of my titration, so I'm going to just go drop by drop, and hopefully, it's sometimes like a gray persists, but I just want that dark blue gone. I'm going to go drop, drop. And that's probably it. Like I can see through my liquid now. I might do one more drop. Yeah, I think I'm good with that. So it's kind of like gray persists, but that dark blue purple is gone. And where I couldn't see through the liquid, I can see through it. So I think I'm going to call that, I'm going to do one more. I think we're good. Yeah. So I'm going to record my new volume, and that is the amount of sodium thiosulfate that I needed to titrate my calcium iodate. So notice, I've got two different equations happening at once. So the concentration of sodium thiosulfate, which is the Na(S2O), what is it, 6? Na(S2O3), okay? So this guy right down here is 0.25 molar. because we know the molarity and we just measured the volume, you can find out the moles of NaS2O3, okay? And then kind of we have two equations happening simultaneously. I now know the moles of this, okay? And if I look at these two equations, the similarity between these two equations is I2. So if I know the moles of this, I can change it into moles of I2. And then I can change moles of I2, because it's the same moles of I2, from I2 to IO3 minus, okay? So there's really going to be two fence and rail fences that have a mole-to-mole ratio, because you're going to have two mole-to-mole ratios because we have two different balanced equations. From there, all right, so again, from here, volume of NaS2O3, and we know the concentration of it, 0.025 molar, so I can find the moles of NaS2O3, or just the S2O3 2 minus in this equation, second equation. So I can go from a 2 to 1 ratio here, and then a, what is it, 3 to 1, 5 to 1 ratio up, or I'm sorry, 3 to 1 ratio in my top equation. So two mole-to-mole ratios, which is going to give us the moles of IO3 2 minus. If you look at your equation, when calcium iodate dissociates, okay, I get 2 iodates for every 1 calcium. So whatever your moles for IO3 are, calcium is going to be half that number of moles. Good? Because we get twice as much IO3 as we do Ca. So now that I know my concentration of Ca and my concentration of IO3, I can then calculate my Ksp. I guess we've been doing moles in your stoichiometry. Again, if you have moles of IO3, we are going to divide that by 10 milliliters because we had exactly 10 milliliters of our solution to get molarity, and then molarity of calcium is half your molarity of iodate. So you can calculate Ksp. And then on the back, there's another calculation you're going to do using like delta H and delta S and delta G, with another equation there at the bottom. So back here, you have this equation, delta G equals negative RT ln K. Okay, so we can calculate delta G from delta H and delta S values. All right. When you look, so you'll take a temperature of all this at the beginning as well. But delta G, we know delta G, we know T. R in this instance is not the gas R, so it's not 0.0821, but it's 8.314, and that is in joules. So you'll need to change your delta G into joules instead of kilojoules. But you're going to calculate, and then we're going to take the inverse of natural log is e raised to the x. Same button on your calculator, it's just the second function of ln is e to the x. And you're going to get a value for k. Hopefully that value is close to the value that you calculated for Ksp on the back. So you're going to compare those two values of k. These values can be used to calculate standard free energy, delta G for the process of actual, and just compare those for me. If you're going to do percent yield, or not percent yield, percent error, so experimental minus accepted, which is going to be the accepted because it's from numbers from a book, divided by accepted. Experimental would be your number minus these. But give me some kind of like comment on how close they are, how far they are, but they're going to be sort of close because the numbers are so ridiculously small. 10 to the negative, really big. Let me see what my calculation was. Like 10 to the negative, I don't know, 6 range, 10 to the negative 4 range. I mean, it's 10 to the negative really small. So it's hard to get that accurate on numbers that small in just a high school chemistry lab. So your error will be big if you calculate error, but just comment on how close they are. They should be relatively close. I think that is it. So your data can be found in a spreadsheet, okay? And it'll be initial, final, there'll be a temperature on there. Your name is next to the data I want you to use. I'll assign you to the groups you typically work with, so if you want to contact them over the weekend. But that's pretty much it. So today's just virtual lab day, and that's it.